recording because it's up. But as I said, this part is actually in the lab. Okay, so thank you for catching that. Um, all right. So what we'll do today is to figure out a few things, okay, which is how does it work, okay? So we'll figure out how this processor works. We are not going to focus on individual instructions yet, okay? At least at the beginning of this class, I just want to make sure that you have all the information that you need in order to get the lab done today, and then we'll move into the actual gritty detail of how the processor actually works. Okay, so with this processor, it has one single RAM component, which is up here. So the RAM component is going to include opcodes in order to specify the operations. The opcodes are in the spreadsheet that we took a look earlier, which is inside here. It is called the opcode table. So in the opcode table, you can see that it only has, I think it's 22 instructions. Okay, so this is definitely a reduced instruction set computer, or otherwise known as a RISC architecture, because you only have like 20 something instructions, of which not every single one is needed, but some are really convenient to have. So that's why it's not even the most minimalist RISC. Okay, this is already including some handy or convenient opcodes. All right. So what we'll do first is we'll go ahead and say, okay, I just want to add two numbers. Okay, how do we do that? If you want to add two numbers, then you can see that, oh, okay, there's one row that corresponds to the add instruction. The mnemonic is add xy. Okay, so now, and then the operation, the description is we perform the actual addition. The result, which is the sum, is going to store to x. So now the question is, what are these things? What is X and Y? So X and Y are registers. Okay, so they each one can be registers A, B, C, or D. So X can be register A, B, C, or D. Register Y or Y, which is a placeholder, can also specify a registers A, B, C, or D. You can add a register to itself, okay, which effectively just doubles the value of that register. So there are four registers. So if you scroll all the way to the top, it explains, register X can be one of the following. Register A is coded as 00 as the XX. Register B is 01 and so on. So the question is now is, what does that mean, the XXYY? So the XXYY is useful when you want to specify the binary opcode to specify that specific operation. So let's just say that you want to perform an addition. I'm going to write it on the whiteboard just so that we can remember what we actually want to do. So let's just say that you want to add CB. Okay. So the first question is, according to the opcode table, which register is being added to which register? So I want you guys to kind of tell me which direction am I adding? Which register is going to store the sum? Register C, that is correct. Okay, so this is the same thing as C plus equal to B. Okay, does everybody understand how to read the compound assignment operator? Okay, plus equal to, minus equal to, times equal to, those are called compound assignment operators, which essentially is the same thing as C equals to C plus B. Okay, kind of like a shorthand. You might notice that I try my best to preserve, right-hand side versus left-hand side in terms of the operands. So you can see how in the C notation, C is the one being changed. It is on the left-hand side of the compound um, assignment operator. In the assembly code, C being the one being changed is also on the left-hand side or being the first operand. So this one, this convention helps you, remember, how do we order the operands. An operand is basically just one of the things that is needed in order for the operation to get the job done. So, but you cannot just specify add CB in the RAM and expect the processor to know what it's supposed to do. So in order to do that, you got a few choices. You can hand assemble the opcode, okay? If you want to hand assemble the opcode, you look at row 21 here, and you say, okay, how do we hand assemble this instruction? 1000 is mandatory. That part is the constant. And then you have to specify XX. So XX as 2 bits will be used to specify register X in the mnemonic, or if you prefer, in the RTL description. So in this case, XX has to represent register C. So do you remember which 2 bits represent register C? So register A is 00. So this would be which? 10 is correct. Okay. So I put a 10 here. What about register B, which is my YY? It's 01, right? So this is 01. So now we have the entire opcode, figure out. It is at 8, 9, okay? Because 1000, according to the hexadecimal conversion table, is 8, and then 1001 is 9 in hexadecimal. So that means I can, if I want to, hand assemble the entire program and put in the actual opcode into the processor and then get it to work. So that means I can now go to this location here. Okay, make sure that you are in the poking tool, and you just say, okay, now I specify the instruction of 8, 9, and now your program has 1 byte programmed. So this is really a good demonstration of the von Neumann or von Neumann architecture, which is basically the idea of you're using RAM not only to store the data that is being processed, but also the instructions to tell the computer what it needs to do or how to get something done. All right. So are we still doing okay so far with all this? Okay. All right. So with a larger or longer program, you don't want to do this like for tens of instructions because it is tedious. If you make a mistake, then the program is not going to work the way that you want it to work. So the best way to do this is to use an assembler. So now I want to introduce you to the assembler. So the assembler is also in the same folder. So if you go to the processor folder, which is shared already with you, then you go to the assembler. There are a few files with the name assembler in it, but only two of those are important. The first one is the assembler manual. Okay, so I highly recommend you guys to download and at least skim through the assembler manual. With Gemini, you can actually point Gemini, at least a gem of Gemini or Notebook LM to the same document so you can actually ask questions about it. Does everybody know what is Notebook LM? Okay, I see some nods. No. Okay, well, if you have not used Notebook LM, it is kind of cool. Okay, so all you have to do is to go to notebooklm.google.com after you sign in as a student, in Los Rios. Okay, so that means you have to sign in with your W7 digit at apps.losrios.edu. It is already paid for, so you have basically a free subscription to Notebook LM. So Notebook LM is kind of cool because it will basically prioritize things that you upload and things that you want to link to it, and then it will do it will do a more general search if it cannot find any information within the files that you specify. So with this, I can now go to Drive, right? Because everything is inside my Drive. I can see my opcode table. I definitely want that. So I'm going to click Insert here. So now we have opcode table as a part of the resources. And I'm going to click in another one. Okay, so I'm going to go to Drive again. But this time I'm going to have to go be a little bit more specific. So from your perspective, it's going to be a shared drive. But from my perspective, it is my own drive. So I go to CISP310, go to the shared folder, go to the processor subfolder, and then I look up um, assembler manual. Okay, so click that, and then click insert. You can also upload the notes, that I have you guys to read in the class. You can also link lecture recordings to this whole thing. So you can basically put in a whole bunch of resources into the resources of Notebook LM, and then you can start to ask questions about it. So it has already picked a pretty good name about this, and we are ready to kind of ask questions about it. Okay, so with only the opcode table and the assembler manual uploaded or linked to Notebook LM, I can ask you the same question. Okay, what is the opcode of add CB, and how do we figure that out? Okay, in other words, I'm testing whether Notebook LM understands the document just by themselves, okay, without any extra resources, to see whether it is a helpful tool for you guys to study and also to understand the material of this class. So I'm going to give it a try, okay? So I would ask you to, okay, show me how to assemble the instruction or the mnemonic, but I think it understands this is a mnemonic. Add CB into a byte of, oops, okay, so into a byte of opcode. Okay, press the enter key. All right, let's check out whether it is doing this correctly. So it found the opcode table, and it has references too. So when you click on these, not click, but when you hover over the references, it would actually tell you where it got that information. So you figure out it is going to be a 1000 XXYY pattern, and then it understands, register A is 00, register B is 01, and so on, blah, 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 blah. And then you figure out that it is 1000, 1001, which is exactly what we just did. Are we okay so far with Notebook LM? I'm not sure about you, but I am somewhat impressed, okay, by Notebook LM, because I did not say anything about, generally speaking, how do we assemble a program in assembly language, okay? So it just knows how to make association between those two documents and figure all this out by itself. All right. So anyway, this is a great resource. Okay, I would highly recommend you guys to experiment with Notebook LM, especially with conjunction with lecture recording for this class. I mean, how many other classes are you taking where the professor would actually give you the lecture recording after each and every lecture? Not a whole lot, right? So you have that resource available to you, and you can link the recording to Notebook LM. Okay, it would actually use the content in the video recording. It cannot really see anything, but it would use the words that I use to describe stuff, and it will still be helpful. You can also add your own notes. Okay, so you can go to add note here and add your own note, your own understanding of the material as a resource to Notebook LM. So this is also quote unquote a note taking, you know, um, I guess your resource. Okay, you can use this for note taking in addition to what you just write down here. When you go home, you basically review what you have written down during class, and then you can use the add note feature here, or you can use a laptop computer during class to basically add note to your Notebook LM resource. So I'm just trying to introduce AI related resources that I think will be helpful. Okay, if not for anything else, okay, if you experience this and you find it useful and you use it and you remember how to use it, in a job interview, you can say, okay, I know how to make use of AI tools to help me understand concepts in a much more effective way compared to just reading by myself. Okay, that is going to be actually a good thing to tell your potential employer. All right, so we're going to leave this alone for the time being because I want to show you how to use the assembler. So the assembler is nothing more than a spreadsheet. So I'm going to have to tell people at least once, okay, do not download this document or download this Google Sheets into Excel and expect it to work in Excel. It works only as a Google Sheet when it is in a browser. So there's no way to download it to make it work locally. All right? Because every semester somebody will try to download it as an Excel file and expect it to work. It does not work that way. Okay? It does need to remain as a Google Sheets. So the first thing you want to do is to go to the source tab here or source sheet. You basically highlight the entire column A and press the delete key. So that will delete the existing program here. And then you can now type whatever program that you want to type. So in this case, I just want to know what is add CB. Okay. So you press the enter key. It's going to take a little bit of time for it to go through the assembling. So if you want to know the assembling process and also the intermediate result of assembling, you can go to the assemble tab. So the assemble tab is kind of cool because it shows you column W is the location in memory. In this case, it means at location 00, column X would be the first byte at that location. So in this case, 89, which is also what we figure out, is the content at location 00. Okay. So when your program becomes kind of long, 80, 90 lines long, this is actually quite useful, okay? Other than because otherwise you have to hand assemble every single instruction. Not that you cannot do that, but it is troublesome, okay? It's really cumbersome to have to do that. So this is good. And then the third thing you can do is to go to the RAM file. So the RAM file is a special sheet where the content can be downloaded and it can also be used to update the RAM content in Logisim. So this is the connection to Logisim. Obviously, when the single opcode is 89, I don't really need to go through this process. But when the program gets longer, do you want to really look at all the opcode in the spreadsheet and hand copy everything over to Logisim when the program is hundreds of bytes? Probably not, okay? Not a good use of your time. So what you can do is to go to the RAM file tab or RAM file sheet, go to file, and then just simply go to download, and I would download CSV in this case, and just have to remember where you put it, okay? So I'm just going to put this, I like to name the file to reflect what it does. So this is add.csv. You click save, and now we have that file created. Not a big file, not really useful, but it is the program of it is the RAM image file of that program. So now I can switch back to Logisim. So let's just say that I click a reset button and reset everything. Okay, Control R would do the same thing. So you can see how the RAM content is going back to all zeros. So now I can right click on the RAM, go to load image, look for that file, which is add.csv in the temp folder for me, click open, and nothing happens. Hmm. Oh, there we go. It just took a while. Took a lot longer than I thought it would, but it does happen. So this is the process, okay? At some point in time, I will give you a even better tool so that you don't have to go back and forth, between the spreadsheet and Logisim. But for the time being, this is going to be okay. Are we doing okay so far? Okay. So I did, okay, implement the entire assembler using Google Sheets, um, which also means for anyone who's curious of how it is done, it is open sourced. Okay, so when you look at the assembler, you can actually go to every single sheet. Most of the magic is in the assemble tab. Okay, so you can actually look at all the equations of the assemble tab, and this is actually kind of long. Okay, this is the full length of that particular formula, which is not long. Okay, it's just kind of long. So you have all of these things, and there are some hidden tabs too. So when you go to, I'm not sure how to display the hidden tabs. Um, anyway, it is open sourced. You can go to extensions because there are certain things I can't really do using a spreadsheet formula. So there are certain things I really have to drop down to Google Apps Script. So for those of you who are interested in, how that is done, you can go to extensions, click on App Scripts, and it will show you all the Google App Script stuff. I have a little do post thing which is not important for the time being, but it will be important later. There's the assemble function. There is a RPN, reverse Polish notation evaluation thing, and so on. So this is not important unless you're curious. Okay. So for people who are curious, you can look into how the assembler is done using a spreadsheet. Otherwise, you just use the regular interface and don't you don't have to look into it. Are we good so far? All right. So what I have just done is to describe how to use quote unquote the entire tool chain, starting with opcode table, which is a description of all the instructions that are available, to the assembler, and also to make a connection between the assembler using the RAM file tab to connect back to Logisim so that whatever program it assembles, the image file can be downloaded onto your computer, and then you can specify that as a image for the RAM component in Logisim. Okay, so that's basically what I have done, up to this point, which is about half an hour. So now the question is, okay, now that we have this program loaded, how does the instruction execute? Okay, so this is actually really important. Okay, I cannot overemphasize, the importance of this part of the class. So I'll do it once, and then I'll give you some recommendations of what you can do. So this is a complicated thing, has a lot of stuff in it, right? But when you look at the actual quote unquote active components, there are really only a few, okay? Which means the first thing I recommend you to do is to download the PDF. Okay, remember the PDF that I talked about earlier? Okay, so I would recommend that you download that PDF and then just highlight, okay, color code the actual super duper important components, because your analysis of how an instruction executes start with those important components. In terms of the names of the components that are important, the registers are important, and then RAM is important. And so same with the ROM. Okay, so those are the three types of components that are super helpful, super important. So on the surface, we have one register right here. It is called PC, or the program counter. This is one of the most important registers in order to understand how the processor works. So PC is one, and I would certainly try to, kind of color code it once you have the map, because being able to find the program counter quickly is actually helpful. And then we have the instruction register. Okay, the instruction register is located here. It is kind of useful, but it's only useful in a particular phase of the execution cycle of an instruction. So it's good to know where to find it, but I would say, its importance is limited. Okay. And then we have the register bank. This is the register bank. It is seen as one single device here, but when you right click and say view register bank, this is where the registers A, B, C, and D are located. Okay. So the register bank is going to serve two purposes. Um, Basically, it presents an interface to the rest of the processor. You can specify a register as an output. You can specify a register as the other output. You can have up to two outputs from the register bank, and these are specified as register output 0, register output 1 in the diagram. You can also update one register, okay? So the one register that you want to update is going through the interface of reg in or register in. But you go like, but which register is register output 0? Which register is register output 1? And which register is actually getting updated? Those are selected, okay? So register output 0 select is telling the mechanism which one of the four registers, A, B, C, or D, is output register 0 of the register bank. And then register output 1 select is telling the mechanism which one of the four registers is presented as register output 1 of the register bank. Are we doing okay so far? There are four internal registers, A, B, C, and D. They are addressable by your opcode, but which one becomes the register output 0 and which one becomes register output 1 depends on what you tell the register bank. Same thing with which register is potentially getting updated. It is specified by register input select. So that will help route um, the enable to one of the four registers in order for that register to be updated. Are we still doing okay so far? Okay. And you look at this diagram, I hope you recognize a few things, right? Input pins and output pins. Okay, those are pretty easy. So there's an input pin here, output pins. There are four over here. Those are really only for um, debugging purposes. So for the most part, they're not really useful in the circuit. And then you have register output 0, register output 1 as output registers. And then you have the select as all the inputs into the circuit. And then we have the four registers. Okay, so I'm going to highlight the four registers. So we've got register A, register B, register C, register D. And then we have the multiplexers. Okay, this is one multiplexer. This is another multiplexer. This is why we talked about multiplexers and demultiplexers in the previous two classes, okay? Because those are the important routing components inside the processor. Without understanding those two, we can't really understand how the processor works in general. Then you guys look at this thing over here, and you go like, attack. We never talked about what is a decoder. That is correct. We actually did not say anything about a decoder because it's easy to describe what a decoder is. A decoder is a demultiplexer with an input of a constant 1. That's it. So if you understand and remember what a demultiplexer is, a decoder is a special case of a demultiplexer. Okay? Are we still doing okay so far? Okay? So, do I expect you to remember everything that I'm talking about today? No. And that's why I will make some suggestions of activities that you can do in order to let that stuff sink in. And I would say every semester, certain people decide that what I recommend is not useful, and then exam two comes along, and those people do not usually do very well in exam two. So I would say, at least do a few of the activities that I recommend. All right, so getting back to the main circuit, there we go. So you can also see there are lots of multiplexer, 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 demultiplexer, demultiplexer, and so on. Okay, so that means even though the circuit looks really busy, it's made out of components for the most part that we already know. Since we are on the in the process of identifying registers, this is another register. This is the flags register, which is not going to come in, which is not going to be useful until I would say give it 2 or 3 more weeks. Okay, so for the time being, it is not one of the components that we really have to track. Here's the RAM component, okay, which is useful. Okay, so we want to definitely be able to track the RAM component, and we want to understand how it works. And then here we have a ROM component, okay? And then we have another register here. This is microcode pointer, okay? So the U of ucoder is actually ucode pointer is micro, okay? Because the Greek letter for micro is mu, and mu looks like a U with a long left-hand edge. So, most people use the letter U to approximate micro. So this is a microcode pointer. So now I have just identified most of the main components, okay? And then you can see I use splitters a lot. So the output of this ROM is going through this splitter to split into a few things. And then one of those things, which is microcode data, is over here, and it is further split into even more stuff. Okay, so each one of these is called a tunnel. The thing about tunnel is um, that all the tunnels of exactly the same name, they are logically connected. Okay, let me give you an example. You can see PCEN here is a tunnel. So that means this PCEN is a tunnel and this PCEN is a tunnel. They are just logically connected. Okay. So the use of tunnel is it serves two purposes. One is we don't end up with wires flying everywhere, okay, making things really, really hard to read. Two, you can also use a name associated with a wire, so it is kind of self-documenting a little bit. Okay. All right. And then on top of all of those, we have the usual logic gates. Okay. So we have one logic gate here that is a AND gate. We have one logic gate here, which is the OR gate, and so on. So those are the main components that we have. This is another AND gate over here, blah, 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 and so on. All right. So now we are ready to take a look at how does the processor actually execute instructions that are stored in RAM. Okay, so this is where things have to become a little bit complicated, and there will be some terms that I introduce in this class, and you might need to kind of jot down some notes, okay, because those terms will be referred to again and again. So the first thing we need to do is to remember, where do we start the analysis? The analysis always start with the microcode pointer. This is the starting point of analyzing how the processor executes instruction. So we always start with the microcode pointer. The microcode pointer, when the processor is reset, the microcode pointer, like all the other registers, will be reset to 0. Okay? So now we say, okay, so what is the microcode pointer pointing to? So you look at the output of the microcode pointer, it connects to the A port of the ROM component. In other words, the microcode pointer specifies the address of which location of the ROM do we want to pay attention to. Okay, so now we look at the ROM component. This ROM component is always selected. You can see how the chip select is connected to a constant of 1, which means it is always selected. It is always active. This is location 0 of the ROM. So each location of the ROM, sometimes I call it a slice. Okay, I call it a slice because it is specifying what to do with the processor at a particular slice of time. So each location of the ROM, sometimes I also use the term of a slice to describe it. So at this point, the address is 000, but the actual content of that location is 1080007 in hexadecimal, which if you want to, you can expand that all the way to the individual bits, which is usually not entirely necessary because you have all the tunnels doing all the work for you. So now we want to analyze and go like, okay, but what does it actually do? Okay, well, you can now look at all the other components and find out which one is active. Okay, in other words, we're now looking for active stuff, the stuff that is being used. So you look at the registers. Okay, you look at this PC, the program counter. Does it look like that I'm going to change the program counter in this case? People in the back, do you want me to zoom in a little bit, or is this actually okay? You want me to zoom in? Zoom in? Okay, we can zoom in a little bit. Okay, so I cannot zoom in too much because if I zoom in too much, then I have to scroll a lot around, and that can be a little bit confusing as well. Okay, so maybe this is good. Okay, excellent. All right. So when we look at the program counter as a register, does it look like it is going to be updated in the next rising edge of the clock? How do we know whether it is going to be updated or not? So do you remember a register is a multi-bit D flip-flop, right? And we talked about an edge sensitive and level sensitive D flip flop. So under what condition is a register going to be updated? Rising edge of the clock is 1, and what does EN represent? Enable. Okay, so how does that factor in to whether a register is going to update or not? What do we need in order for a register to update? So this is going back to material from the previous 2 classes. Do we remember? Remember has to be a 1, right? Is this enable 1 or 0? You go like, how can we possibly tell? Because it's either dark green or light green. Okay, so light green is what? Light green is a 1, dark green is a 0. So that means this enable is turned off. Okay, it's a 0. So if enable is a 0, it means the register is not going to update on the next rising edge, which means I can forget about it for now. Okay. Now, is someone else going to read the output of the program counter? Possibly. Okay. But we know the program counter is not getting updated. Okay. Which means I don't have any further questions at this point because I cannot tell who is going to use the program counter or whether there's someone using the program counter. We look at the register, instruction register. Is it going to be updated? We do the same analysis. Is it going to be updated? Yes, because enable is bright green, it is a 1, which means it is going to update on the next rising edge. The next rising edge is the next transition because we can see the clock is dark green right now, which is a 0. So that means the next transition of the clock is going to turn it into a 1, which means we're going to have a rising edge. Okay. But for now, everything is static. Okay. Everything is, the clock is a 0. So we just take a note of, the instruction register will be updated. Now, that by itself should prompt you to ask yourself a question. What question would that be? So you already know the instruction register is going to be updated. So what is the natural question to ask? Okay, and how do you figure out what it is going to be updated to? What do you need to track down? Which port of a register specifies the content that it is going to be updated to? There are only so many ports, right? So there's the D port, there's the Q port, there's the EN enable port, there's the clock, and there's the reset. So which port do we need to track down in order to figure out how it is going to be updated? Sorry? The D port. Very good. Okay, so the D port is what we need to track down. So this is where the fun starts. Okay, if you are doing this the first time, I would also recommend using a piece of paper or you're starting a text editor just so that you can remember what you're tracking down because you can probably get lost in the details pretty quickly if you don't track. So we want to track down, okay, who is supplying the information to update the instruction register. So this is also a good time to mention by this time, you really need to know which port is which port and how a register works in general. If not, at least know where to find that information, okay? Because that's how we can figure out how the entire processor is going to work. So we have to track down this connection here, okay? So I can select the entire node, and you can see it kind of goes everywhere. Well, we'll track down all of those connections and cross out the ones that do not actually are not useful. So what about this connection here? Do you think this demultiplexer is going to specify the content for the instruction register to update? And why not? Because it is not enabled. It is disabled, okay? Because our O0EN is dark green. It is a zero, so the demultiplexer is turned off. Okay. Now remember, with a demultiplexer, when it's quote unquote turned off, the output can either be a zero or a tri-state. So you kind of have to make sure that it is floating. Disable output is floating, so that means this component, it is as if it's not even here. Okay, so that was a dead end. So we will track down the other connections. What about this multiplexer here? Well, that's is this part here the input or the output of a multiplexer? So which one is which one? Okay, because we know that one of them is a multi-input, one single output, and the other one is one single input and multiple output. This is a multiplexer. So which one is it? It's multi-input, one single output, which means what I'm pointing at using the pokey finger right here, that's one of the input ports. Can an input port output something? The question answers itself, right? No? Because what I asked was, can an input port output? Okay, and the answer is no. Otherwise, it wouldn't be called an input port. Okay, so that means, oh, okay, we got another dead end. Okay, so we look at some other stuff. Okay, what else? Where else is it connected to? We know this is a dead end. We just explore that. So now we scroll all the way up here, and we go like, okay, this is also a dead end because this is an output pin. The only port to an output pin is an input. So that means this D port is not going to update the content of this particular node. So now we have to get here. Okay, it looks like we are ending up with a connection to a RAM component. Okay, so when you get to a RAM component, what is the first question to ask? Is it chip selected or enabled, right? So you look at the enable port here. Okay, so you look at the enable or chip select. It is a 1. So what is that telling us? Is the RAM component being used, or it is disabled and it is as if the RAM component is not even on the circuit? It's being used, right? Okay. So if the RAM component is being used, what are the natural 3 additional questions to answer? So which direction, right? Are we reading from the RAM component or are we writing to the RAM component? Very good. So let's answer that question. Which of these ports tell us whether we are reading or writing to the RAM component? Load, LD. Okay, very good. So we just kind of hover our mouse pointer over here, and it tells us if 1 loading memory to output. And it is a 1 right now. So we are reading from the RAM. Okay. So that means the RAM component is going to specify something at the D port, which eventually will end up at the instruction register to update the instruction register. But I said there were 3 additional questions. We just answered 1, or actually 2 of those 3 questions. Okay, so the 3 questions that you should ask is um, where is the D port going? Okay, who's connected to the D port? And then the third question is who's connected to the A port? In other words, who is telling the RAM component which location is being addressed? Is that okay? All right. Okay, so let me check first. Okay, do you think those are quote unquote natural questions to ask based on what the component can do? Okay, I see some nods. Okay, very good. Because that is how we do reasoning. Okay, I cannot teach reasoning. Okay, because to me those are just natural things that my mind would do. Okay, if I know that the RAM component is selected, I just come up with these questions. Okay, what are we doing with it? Who is telling me which location we need to take a look at, and are we changing that location, or are we reading that location, and who's reading it if we are reading it? So those are all the questions that are natural to me. What if those questions are not natural to you? What do you do? Hmm? Exactly. Okay. And this lecture is being recorded, right? And we have Notebook LM. So you can now go to Notebook LM and you say, summarize what questions to ask for each component based on text lecture. I'm pretty sure it can do a summary. Okay. But I would gently, say that it's a better thing to do if you are to figure that out instead of copying what I do. Okay, because I want to train you guys so that you can actually do all of this. So what kind of skill is this? It's critical thinking. This is actually just a form of critical thinking because you're just saying, okay, if this thing is active, okay, why is it active? How are we using it? All those are questions that you have to kind of ask yourself. Okay. So, what do we tell people who have a general because of education? So, this is not because of those people, but because of how they're educated. So, what do we tell people who say, I have to be told what to do next? I wasn't educated or trained to think like that. So, what do we do? What do we tell those people? Because I know some of you know what questions to ask already. So, what do you think is a good way to tell the people who say, but I don't do that? Okay, this is not how I was trained to do. I was trained to follow instructions. Okay, I have one suggestion, which may not sound kind at all. Okay, the suggestion is don't wait for someone to tell you what to do. Okay, and instead start asking questions and attempt to answer those questions yourself. It has to start somewhere because there are no jobs left where someone can just expect to follow instructions and get paid for that. Does that sound really harsh? Unfortunately, it is reality. So I want you guys to know reality here at this point instead of later on, instead of waiting until you get your bachelor's degree and have a student loan, then you real and that would be a brutal point of time to realize what I just said. Okay, understanding it now is actually not a big deal. Okay, because who is born to have all of these cognitive skills, critical thinking, problem solving, and all that good stuff? Nobody. It's all trained. Okay, those are all skills. So we can all learn how to do that. All right. So to answer this question, okay, so we still got the third question not answered. Okay, we got the first two questions already answered, which is we are reading because load is a one. We know the D port is connected to the D port of the instruction register, which means whatever the content is outputting is going to update the instruction register. But we still haven't answered the third question, which is who is telling me where to read? So what do we do? Well, there's no easy way to answer that question. You just have to track it down. Okay. So you look at the A port, it goes all the way to the output of this multiplexer. So now what do we do? We know this is a multiplexer. What does a multiplexer do? Generally speaking, it has multiple inputs, one single output. So the job of a multiplexer is to select up to one input and connect it to the output. We know the output now. Okay, this is the output. So what is my next thing to do to track down who is ultimately connected to the A port of RAM? How do we answer that question? Say again? So we have to follow along, right? But it has two inputs. Which one should I follow? So what dictates which input connects to the output of a multiplexer? Why is there a little gray dot? Okay, why is there a gray dot over here? What does the gray dot tell us? Yep, because below the gray dot is the select. Okay, so in this case, it's a one bit select because you only got two inputs. So if the select is a zero, you're selecting input zero. If the select is a one, you're selecting, guess what? Input one, right? So can someone tell me what is the select? Is it a zero or is it a one? It is a one. So between the two inputs, which one should I track? This one, this one, right? It says right here, input one matches one as a select. Okay, so that is what we do in this class at this point. Okay, you have to be able to track down stuff based on how the individual smaller components work. Okay. All right, so we track it down. Okay, we have to scroll again. And oh, look at this. It is coming out of the program counter. So the program counter is actually specifying what address of RAM we are interested in. The content at that location is used to update the register instruction register. That is what we are about to do. Yes, say again. Well, it is not updating now, right? Because it has a dark green going into the enable, so it's not updating yet. It will update later, okay? So we are not updating yet. Um, yeah, we'll see in a later part how it is going to be updated. Okay. So right now, if I were to use RTL to describe what is going to happen on the next rising edge, how will we describe it? So I'm going to use IR, to represent instruction register. It is going to be updated. So excuse me. So I'm going to borrow the assignment operator from C++ so that the left-hand side is going to be the one being updated. So what is on the right-hand side? On the right-hand side is RAM, okay, which is memory. So in a way, I'm actually doing this. Whatever the program counter is pointing to, the content that the program counter is pointing to in RAM is used to update the instruction register. So this would be the RTL that I would use to describe what is going to happen when we have a rising edge. Okay, just a quick quiz right here. What is RTL? Register transfer language. And that's why I told you guys to write it down earlier because we are using it again and again. Okay. The reason why it's called RTL is because what is IR? It's an abbreviation of instruction register, right? What is the program counter? What type of device is it? It is a register, right? So this notation is relating the registers together to specify what the processor is going to do. And that's why it's called RTL, Register Transfer Language. Okay, cool. So when I type Control T on the keyboard, I am triggering the clock to change its state. So we are expecting the instruction register to become what? What was what did I put into location 00 earlier? 89 in hexadecimal, right? And it is being output at the D port of RAM. So that means I think the instruction register should become 89 when I click Control T, which causes one transition of the clock. So that's what I'll do. Control T right here, and it becomes 89. Okay. So this part is called the fetch phase of instruction execution. That is actually in the notes. Okay. So I can point back to the notes. So this way you don't have to write down stuff unnecessarily. So if I go back to my notes, and how to track instruction execution in TTP, I believe that will tell you, all the terms. Okay, so it is helpful to read it. Okay, if you say I don't want to read Anything that tech writes, because it's too hard for me to understand, upload it to Notebook LM. And then ask Notebook LM to explain it to you in any language, in any complexity of language. Okay, so you can say, people can say, okay, my English is not really particularly good. Can you explain this in simpler English? Notebook LM understands what that means, okay, and it will be able to explain it in simpler terms, okay. You can also use Notebook LM and say, okay, I want to translate this to my native tongue, so I can specify, okay, can you explain this to me in Chinese? If you don't think that is, if you think I'm just pulling pulling your leg, I'll do this, okay? Can you explain this in Chinese? Let's see. Okay. Yep, it does. Not that it's helpful because the for technical terms, I actually don't understand a single thing that is spewing out. I can read it, I can understand every single character, but since I am not trained to read all the technical terms in Chinese, this is useless to me. But it is, I'm just demonstrating that it is possible. Okay, it's doable. It is cool. All right, getting back to here. So now we're going to have a falling edge. Only one register, which is the microcode pointer, is sensitive to a falling edge because it is specified like that. The trigger is on the falling edge. So no other register, not RAM, is going to do a single thing on the falling edge except for the microcode pointer. Okay, so we know that the microcode pointer is now going to be updated because it is always enabled, because this enable is connected to a constant of 1. It is always going to update on a falling edge. We're going to have a falling edge because clock is currently a 1, which means the next transition will go to a 0. We have a falling edge. So what is the next question to ask? This is a register. We know it's going to up. Yep. How is it going to be updated, right? So which port do we track? The D port. Yep. So we track down the D port, which is this guy. We go like, oh, it's coming out of a multiplexer again. I hate this. Okay, but it's not too bad. Okay, it's only a two input multiplexer. So which input of the multiplexer should I track? The top or the bottom? The top is labeled 0. Is the select 0 or 1? It is a 1, right? So we track input 1. So which is this one here. We track it. We track it. It's coming out of an adder. Okay, this is an adder because you can click on it to find out what it is. Come on. Nope. Okay, we have to use a select here. So it is an adder, okay? So it is adding the two inputs here and also K0, okay? Remember, I keep telling you guys, well, we can assume K0 is a 0 most of the time. Well, this is one of the cases where K0 is a 1, okay? It is just how the circuit is connected, okay? So what this circuit is really doing is we are adding 0 to this whole thing here, but because K0 is a 1, we're really effectively just adding 1 to whatever is the input. Um, where's the input connected to? The microcode pointer itself. So effectively, we are incrementing the microcode pointer. So on the falling edge, the microcode pointer will simply increment to 0, 0, 1. Okay, so that's not the most glamorous thing that we do, but we can see that, oh, look at this. The address of the ROM is now 001. We are addressing location 001, which has a different content compared to 000. Okay, the next edge is going to be a rising edge, which means, okay, we know that we are not going to update the microcode pointer here. We have a rising edge, so we have to figure out what is going to update this time. So we do the same thing. There are only so many registers, right? There's a program counter, there's the instruction register, there's RAM, and there's the microcode pointer. 4 items, right? How do you train yourself to be able to find those registers quickly? Download the PDF, get your highlighter, okay, and just circle, okay, those components that are good starting points for the analysis of how the processor get things done. There are only like 4 or 5 of those things, so I don't think it would take you a long time to circle those things in with a highlighter. Okay, look at this. The program counter is going to get updated this time. So what do I track? The D port. The D port is coming out of the multiplexer. The multiplexer has a dark green here. So that means we have to track down input 0. Input 0 goes back to a mechanism that looks almost exactly the same as what we saw earlier, which means the program counter is now going to be incremented. Okay, so this is the incrementing of the program counter, which means we have something that looks like this, right? PC is PC plus 1, okay? And nothing else is getting changed in this case. So not not exactly super cool, but this is all we need to do. So the program count is updated to 1. So now we are going back to the microcode pointer, because every time we have a falling edge, the microcode pointer is the one that is getting changed. So we have to go back to the microcode pointer. So, well, it is always going to be updated on a falling edge. So we just have to track down how it is going to be updated. So we can see how the D port is connected to the multiplexer, but this time the multiplexer has a dark green for the select, which means we have to track down input 0. So we track down input 0, and what do we see? We see a splitter. The splitter, oh, by the way, I can read this out because people in the back cannot see it. This reads 03 or 0-23. This reads 4 to 11. So that means bit 0 to bit 3 are really just a constant of 0. What about bit 4 to bit 11? It's coming from the tunnel called instruction, and we can see the other end of that tunnel, which is the output of the instruction register. So that means 89 in hexadecimal will be used as bit 4 to bit 11 of the microcode pointer, and then 4 zeros will be used as bit 0 to bit 3. Okay, so that means after we update, microcode pointer should become 890. So this is called the decode phase of the instruction execution cycle. It's called decode because what we are doing is we are looking at the opcode, and then we are looking up basically the ROM and say, okay, tell me how this instruction is going to be to work with all the individual components. And that's why it's called a decode cycle. So we have a control T, and look at this, okay? It is now at 890, and we are now addressing 890. So at this point, we only got about 2 more minutes, so I'm gonna have to go a little bit fast, but it really is the same kind of um, analysis. So we look at the register bank and you go like, okay, do we see anything that is bright green? Yes, we do see something that's bright green. So now we go like, okay, what does that mean? This is input enable, which means that one of the four registers will be updated. So the natural question to ask is, how is it updated? We have to look at this multiplexer. Okay, so this multiplexer is saying, okay, we are taking input 1 to present to the output. So now we have to look at input 1. Input 1 is coming out of the output of the ALU, the arithmetic and logic unit. So now we have to look into the ALU, and we go like, okay, we were tracking down this thing here. So now we have to track down, who is going to specify this output? Oh, it is coming out of a multiplexer, and then the multiplexer has a select of 000. So that means input 0 of this multiplexer is connected to the actual output, which eventually connects to the register bank. So we click on this thing here. It is coming out of the output of the adder. Okay. And this particular adder does not have any special things about K0, but it does have to connect to the first input and the second input. So now you have to track down each one of these individually. This one is coming out of this demultiplexer. This demultiplexer has the same select as the other multiplexer here, which is 0, 0, 0. So we know that this connects to this. And then we track down the second input to the adder. We also can find out that, oh, okay, so this output is indeed connected to this input over here, which means now we have to track down the two inputs of the ALU to find out where it goes. Okay, so getting back here, this is the first input. It's coming out of a demultiplexer. This demultiplexer is now turned on, and the select is 0, 1, which means, oh, okay, so the input is in fact connected to this output. So now we have to track this down and go like, okay, which register connects to this one here? We go into the register bank, we look at this wire, we look at this multiplexer, it has a select of 1, 0, which means this input connects to this output here, which means register C connects to input 1 of the ALU. Is that okay? So likewise, because we are running out of time, so likewise, we know register B connects to input 2 of the ALU, which means the ALU is adding register B and register C and come up with the output. The output of the ALU eventually connects back to the register input here. So now the question is, which one of the registers is going to be updated? So we have to track that down, right? So you go like, oh, this is not helpful. It connects to all four registers. It connects to the D port of all four registers. But only one out of the four registers is enabled. Which one is enabled? Follow the bright green line, right? So which one is going to be updated? Register C. So is that consistent with what we think it should do? There we go. So this is how we track down how one instruction works. And you guys go like, how many instructions do we have to track down? 22. But the 22 instructions are organized in families, okay? So add, subtract, compare, and or, they're in the same family, okay? You only have to try one to understand how it works, okay? So that means the actual number of instructions that you have to track down is significantly less than 20. But if you don't do this, if you don't try to do the same thing here with the other instructions, you're not going to be able to understand how the processor works, which means the second exam is going to be brutal for those people. Yes. Huh? You are basically, I'm okay. Do you, as kids, do you I really lusted after those little V8 engine, the plastic V8 engine with a transparent engine block, because I want to know how the pistons work and how the crankshaft works, right? This is it. You have a tiny little crank called Control T, and you turn it a little bit, and you observe how the valve opens and closes and stuff like that. Except it actually works. You can actually get programs to run within this little processor with only 256 bytes of code. So it actually is a tiny little V8 engine that runs. Just have to give it gas and get it started. Yep. And the other thing that's great about this, is um, we are basically, we are freezing a single frame in time. So you have all the time in the world to actually figure out how everything is interconnected just for that one single moment of time. And then when we have the transition, all the registers change at the same time, because the rising edge affects all the registers except for the microcode pointer. So that's why this is I think this is a great way to at least gain a general understanding of what is inside the processor. Is this a standardized processor? No, it's a very simple processor, but it does illustrate what goes on inside the processor when it runs. So I don't know about you, but I really like doing this sort of thing. All right, we do have a lab today. So the lab today is mostly focusing on just the tool chain. So it doesn't ask you, too many questions about the inside the processor. So your quiz or lab today is called familiarizing with the TTP toolchain, and then the access code is TTPASM, which stands for Tax Toy Processor Assembler. All right, so there you go. I just have to publish it. So by the time you get to the lab, you guys can get started. I will see you in a few minutes.